Assalamu alaikum. This is Physics 731. In this lecture, we will discuss the eigenfunction expansions of green functions. Now consider the elliptic differential equation given by del square psi plus f of x plus lambda psi x equals 0 and the boundary condition of psi at the surface satisfies homogeneous boundary conditions. Now let us replace in this equation lambda by an eigenvalue and psi by psi sub n and some eigenfunctions. So psi sub n is well behaved in this case, finite and continuous. Now rewrite this as del square psi sub n plus f of x plus lambda n psi sub n of x. We'll assume that the wave function is orthonormal, that's psi m star psi n x d3x integration over v is delta mn, which means that psi sub n, this set of functions form a complete set. Now let's write the differential equation in terms of a green function, which is del square sub x g of x x prime plus f of x plus lambda g of x x prime equal minus 4 by delta x minus x0, and assuming that lambda is not equal to lambda sub n. Now suppose g of x x prime satisfies the same boundary conditions as the above eigenfunctions. Let's expand g in terms of psi n. G of x x prime is the summation of a sub n of x prime psi sub n of x, and then substitute this expression for g in this equation, which is del square g plus such and such equal minus 4 by delta x minus x prime. Now perform the calculation, we get this expression a sub n. The operator acts on psi because psi is function of x and the differentiation is with respect to x, so we get this expression. Now simplify, we finally reach to this expression, or change the dummy to m, which is a sub m of x prime lambda minus psi m minus 4 delta x minus x prime. Now let's multiply this from right by integration over v psi n star x t3x and perform the integration. This is delta n m and this is psi n of x prime. So we get a sub n of x prime of lambda minus lambda n equal minus 4 by psi n star of x prime, or a sub n of x prime is 4 by psi n star of x prime over lambda n minus lambda. Now substitute this in the expansion for the Green's function, we get this expression. If we have a continuous spectrum, we convert this summation into integrations. Note that for lambda equals 0, we get this expression. Now we have this expression. If we put f of x equals 0 and lambda equals 0, this is the above equation reduced to the Poisson's equation. Let's take an example, the wave equation or Helmholtz equation, this one, which is del square plus k square psi sub n of x equals 0, where k is a continuous, and the eigenfunction is given by this expression psi sub k of x equal 1 over 2 by to the power 3 halves e to I k dot x. This is the eigenfunctions. The orthogonality relation is given by this. Now we have g is 4 by summation over n psi n star psi n of x over lambda n minus lambda where lambda, we assume that lambda is equal to 0. So the infinite space Green's function now has this expression where we convert the summation into integration. Sum over n is 1 over 2 pi to the power 3 halves d3, 1 over 2 pi d, to the power 3 d3 k. So we get this expression. I already derived this in previous lectures. Now let's consider a Dirichlet problem inside a rectangular box by 6 given by this 6 planes A, B, and C. Then we have this equation. This equation reduces to the following form, which is k square lmn psi n lm equals 0, and we know that the solution for this problem is given by square root over 8 ABC. This is the normalized constant sine L by over AX, sine M by over BY, sine M N by over C times Z. L, M, and are integers. In this case, K, L, N, LMN square is given by this expression. We know this actually. This is very easy to derive this. Now the form of J is given by this expression. We have to substitute lambda 0 and lambda n is k square lmn. So we get finally this expression for G. Now let's solve another problem, problem number 15 from the book textbook by Jackson, second edition. The problem is concerned about the Dirichlet problem of two grounded planes. It's one located at z equals 0 and the other is located at z equal L. We have to prove that Green's function is given by this expression in cylindrical system of coordinates, and we have to change this also into another form. Now this is the problem we want to solve. We already solved this problem with the chart here. Problem number 113 of the textbook. Now we have this equation del square xg sub dx x prime is equal to minus 4 by the x minus x prime. Let's write this in terms of cylindrical coordinates, which is delta rho minus rho prime over rho delta phi minus phi prime delta z minus z prime. But we know that delta phi minus phi prime is 1 over 2 by summation from over m from minus infinity to plus infinity of exponential im of phi minus phi prime. And then for the last one, delta z minus z prime can be written, because we have here 0 and L, can be written as 2 over L, summation from n equal 1 to infinity. It is easy to show this. Sine n by z over L, sine n by z prime over L. Now, assume that the Green's function takes this similar form, which is 1 over by L summation from n to minus infinity up to infinity over n from 1 to infinity e to im phi minus phi prime sine n by over L z sine n by over L z prime times the reduced function j sub m, and it takes two indices, which is function of rho prime. We know that del square in cylindrical coordinates is given by this expression. So operate by this on GD, we get this expression 1 over rho. This guy acts on the rho part here because there is no z or phi part in this del, and the rest gives you the second d. When you operate here on phi and on z, you get this thing. So times G mn. So this should be equal to the right hand side of this once you substitute instead of delta z minus z prime and delta phi minus phi prime, and then equate the coefficients, we get this radial equation. Now, for rho does not equal rho prime, we know that the solution is the modified Bessel functions I sub m and k sub m, and here we have n by over L, so g sub mn is given by this expression. Now the discontinuity, there's a discontinuity in g, we can refer to this equation and integrate at rho equal rho prime minus epsilon up to rho equal rho prime plus epsilon. So this gives us gm n equal 4 pi. Now substitute back in the equation for the Green's function, we get this expression, which is the required form. Now to get an alternative form, let's now use the write the Dirac delta function delta rho minus rho prime over rho by this in terms of the Bessel functions, which is from 0 to infinity k dk g sub m of k rho prime. We already know this relation from previous lectures, and use again the same expression for delta phi, and then g sub d takes this form as we did in the part A, but now instead of g we write f, which is depends on two indices m and k. Now f is function of z and z prime. Substitute back in the equation, we get finally this equation satisfied by this function fmn, and the solution, we know that the solution for this is for z does not equal to z prime is hyperabolic sine kz smaller hyperabolic sine k of L minus z greater is the correct function for this, that's satisfied by this equation. Now collect these terms and put them back in the expression of g sub d, we get the required expression. Thank you.